Initializing the recording device, there it is. Okay, so what are we doing today? Definition of the derivative. By the way, I fixed this. Did you notice on your sheet it says 5, 6, 7? That's wrong. We're at 3 today and 5 tomorrow? No. Tomorrow being Monday. Right? So you might make a note of that. It says 5, 6, 7. What the heck? I don't know what happened there. Yeah, I don't know how to count. I do calculus, so I can't count. It's okay. Yeah. And this is a minor change too, but I always used to call the testing days, the pre-test and the test, AP days, because it's practice AP stuff, right? But I'm going to differentiate between free response AP days and multiple choice AP days eventually. So I changed that up a little too. It doesn't say AP day anymore. Your sheet does, doesn't it? Yeah, it's going to be free response stuff next week, yeah. Alrighty, so let us talk about derivatives. Let's let you know everything about limits, and we can define the... there she is, I knew it. We can define the derivative as a limit. That's a good thing, yes? Here we go. Kindly consider the following function. Let's see. You guys ever watch Bill Nye? The taxi? He always just says this, right? Kindly consider the following. Kindly consider the following. H of t is 1024 minus 16t squared. Is a displacement function or a height function from, I don't know, a bowling ball that threw off a roof.
Is that a 1024?
Yeah, 1024. This is h of t, the height of my grapefruit, or my bowling ball. Let's make it a bowling ball. That I dropped off the roof of a building 1,024 feet high. Roughly, I don't know, what is that, 100 stories or something, right? And it's falling down due to gravity. This is g over 2, if g is negative 32 feet per second, right? All right, so time is in seconds, h is in feet, and this is a bowling ball falling on somebody's head, okay? Now, what does this graph look like? A parabola, right. Is that how the bowling ball is moving, in a parabolic trajectory? No, right. What I'm saying is I just dropped it, so it's going straight down, okay? So don't get confused between the graph of h of t and the trajectory of the ball, okay? It's not the same thing. Okay, so what point is this? Do you know it? What's the y-intercept or the h-intercept? Right, so plug in t would be what here? 0, so what do you get? 1024, right. All right, now how long does it take to hit the ground? What's the t-intercept when h is 0? Well, let's find out. 0 equals 1024 minus 16t squared. I'm just plugging in 0 for h to see when it hits the ground. How do you solve this algebraically? First step? Okay, so what's the first step? Okay, negative 1024 equals negative 16t squared. Now what? All right, the negatives cancel, don't they? And let's see, half of this is 512, half of that is 256, half of that is 128, and half of that is 64. So t is, and usually we say plus or minus 8, but in this case we're talking about a domain from 0 on, so I'm going to ignore the negative answer, okay? So in 8 seconds it hits the ground. Okay. Well, what's this point? Let's say when t is 1. Well, if you plug in 1, I think you get 1008, don't you? How about this point when t is 2? Let's see, 2 squared is 4, times 16 is 64. From this would be 960, right? Do you need a HAL to do arithmetic? Hopefully not. All right, what about, let's go to 4. What about when t is 4? This is not necessarily to scale. If I plug in 4, 4 squared is 16. 16 times 16 is 256. Yeah, from 1024 is... is that right? Well, I think it's 768. We can check that later. Okay, now here's my question. What's the slope of the line that goes through these 2 points? The slope of the line that goes through this point when t equals 1, and this point when t equals 8. Change y over change in x, except it's not y and x, so There you go, good. All right, so let's calculate delta H over delta T for T goes from 1 to 8. So how do you do a slope? How do you calculate slope? All right, so let me start you up. 1,008 minus 0 over 1 minus 8 happens to be negative 144. Now, what are the units? Feet per second, right? I told you H was in feet and T is in seconds, so this is a velocity, isn't it? All right, that's a displacement curve, but the slope of this, what do you call a line that goes through the curve? It doesn't touch one place, it goes through it. Secant line, right. And what do you call the one that just taps? Tangent line, right? Okay. So the slope of the secant line here is negative 144 feet per second. Okay. How about if we go from this point to this point? Down here. It's not quite a line, but pretend, okay? So from 1 to 4. What's delta H over delta T now? Well, you start off 1,008 minus 768 over 1 minus what? 4. Okay. And that happens to work out to negative 80. Why is it negative, by the way? Well, what does it mean, though, physically, that this velocity is negative? It's a velocity, right? The negative has to do with the frame of reference. Downward is negative, I guess? Okay. All right, let's do it from 1 to 2. Delta H over delta T is 1,008 minus 960 over 1 minus 2, and that works out to negative 48, by the way. Just saving a little time here. You can put that in hell if you want. So what am I doing? Well, notice as this point gets closer and closer to this point, and vice versa, this point's approaching, right? This point. The slope of the secant line is getting really, really close to the slope of the... Do you see what's happening? As delta T goes to 0, delta here, T is 7. Delta T here is 3. Delta T here is 1, right? As delta T gets closer and closer to 0, the secant line slopes approach what? The slope of the what? Tangent line. That's the whole idea. We're gonna define the limit as delta T goes to 0 of the slope of the secant to be the slope of the tangent. That's our definition. And we're going to call the slope of the secant line an average rate of change. Over t equals 1 to 8, the average rate of change was negative 144 feet per second. From t equals 1 to 4, the average rate of change was 80 feet per second. For t equals 1 to 2, the average rate of change is negative 48 feet per second. But the instantaneous rate of change is the slope of the tangent line. The instantaneous rate of change at t equals 1. Guess, what is it? You having a guess? As delta t gets smaller, this is 7. This, I'm talking absolute value. This is 3. This is 1. The answer is getting closer and closer to the tangent line slope. Negative 144, negative 80, negative 48. Guess. What do you think the tangent line slope is? This is a limit. This is limiting toward the tangent line slope. It's getting, in absolute value, smaller and smaller and smaller, isn't it? So guess. Just guess. Anything. Negative 30? Okay, that's my guess. All right? Now, let's see how good that guess is. We're going to now figure out how to find out the exact instantaneous rate of change as delta t goes to 0. See, the problem is, when delta t is 0, this is undefined, right? How do you deal with that? That's a problem. All right, so is everyone seeing what we're doing? We're trying to take slopes of secant lines, getting closer and closer to the tangent line, trying to get a limit. All righty. So let's get a definition of the derivative here. Let's say you have some curve, right? It is any old curve, as long as it's continuous and differentiable and all that fun stuff. Let's make it an easier parabola. How about it goes through 0, 0? So here's my curve. If this is x, what's this? I don't know what this function is. What would I call it? Give it a name. We name functions all the time. How about f of x? G of x, I don't care. F of x, okay. So this is y equals f of x. This is y, this is x. By the way, don't get all excited. It's not always y's and x's, as you see, right? But whatever's on the horizontal tangent, you treat it like x stuff. Whatever's on the vertical tangent, treat it like y stuff, okay? All right, so, but here we went back to the familiar x and y. All right, so let's say I move over a little bit. I take x plus a little bit, plus delta x. This distance is delta x, right? What's the function value up here? At x, we get f of x. At x plus delta x, we get what? Yeah, that f of x plus delta x, that's all. Can you now tell me the slope of this secant line? What is the slope of that secant line? It would be, let's see, I'll start off. F of x plus delta x. So I did it wrong, sorry. Because we're doing like delta y over delta x, right? All right, so this y value minus, I'm taking the y value of this point minus the y value of this point. Is that how you do slope? So what is it? F of x over what? X plus delta x, the x value of this point, minus the x value of this point. Okay. But what is that? What is x plus delta x minus x? That's just delta x. Okay. So we're going to say that that's the slope of the secant line, right? Let me simplify it a little bit. And we said that the limit as delta x goes to 0 is the derivative, the slope of the tangent line. Okay? That's the definition of the derivative. That's f prime at x. That's what it is. Notice all I'm doing is I'm fleshing out what this is. The limit is delta t, well, it's delta x on the other page, goes to 0 of the slope of the secant line. Okay. The limit is delta x goes to 0 of the slope of the secant line. It's the same thing. So this is my definition of the derivative. Okay? F prime of x equals the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. By the way, this has a special name. This is called the difference, because I'm subtracting, quotient, because I'm dividing. It's a very famous quantity, so it has a name. This is the definition of the derivative as the limit of the difference quotient. All right, now, this gets a little bit tedious, writing delta x all over the place. So usually you'll find it in the textbook a little bit differently. You might have seen it this way. Rename delta x as something easy, like h. Okay? The limit as h goes to 0 of f of x plus h minus f of x over h. And again, this is not a plug-in limit, because as h goes to 0, you can't plug it into the denominator, can you? Right? But remember, we can figure out stuff like this sometimes. We've done limits like this. All right, so what I want to do is apply that rule that we just made up, right? We just made up this rule. I want to apply it to this function, so I can get f prime at 1. Yep. I want to know what is f prime at 1. Okay, Gretchen, they want you now. Do not ask for whom the bell tolls, it tolls for thee. It's later. Enjoy. Okay, so, this is what I want to ask. This is the question I really want to ask. I want the slope of the tangent line at 1, right? So, if f of x, what, you need this still? What? Go ahead. All right, so let's say f of x, you know it. It's some function. It's the one I gave you originally. 1,024 minus 16x squared instead of t squared, whatever, same thing. Just tell me about it. Are you good? You got it? This is what you wanted? Okay. So let's say f of x is 1,024 minus 16x squared. The question is, what's f prime at 1? That's what I want to know. Okay? That would be the limit of the secant line slopes as they get closer and closer and closer. The endpoints get closer and closer and closer to the point at t equals 1. I'm using x instead of t here. All right, so let's use this definition. F prime at 1 is the limit as h goes to 0 of the function at 1 plus h minus the function at 1 over h. Okay, I'm going to write that. F prime at 1 is the limit as h goes to 0 of this function, 1024 minus 16 times 1 squared, sorry, wrong, 1 plus h. 1 plus h squared, okay? Minus this whole thing, minus the function at 1, 1024 minus 16 times 1 squared. Okay? All over what? Don't forget. What was the problem? It was over h. That was the problem. I can't plug in 0 here, right? Okay, so you see what I did? I just fleshed out this definition for my function and my x. I put in 1 plus h, I put in 1 wherever I saw x, and I put in the function 1024 minus 16x squared wherever I saw f. So what is f of 1 plus h? Just compose, right? F of 1 plus h is plug in 1 plus h wherever we see x. F of 1 is plug in 1 wherever we see x. Can we simplify this? Maybe this can be done, this limit. Let's see, let's work this out a little bit. The limit, as h approaches 0, let's see, what's the numerator now? Well, do you know how to FOIL this out? You can FOIL this out, 1 plus h squared, right? It's going to be 1024 minus 16 times what? FOIL this out, what do you get? 1 plus 2h plus h squared. Do you know how to FOIL?
Yeah.
When you square a sum, you don't get the sum of the squares. When you square a product, you get the sum of the squares. FOIL it out, 1 plus h times 1 plus h. Right? You get 3 terms, don't you? That's where trinomial factoring comes from. Okay, I'll fix that. Make it. Okay, yeah, that's how I was doing it. And remember, we worked this out already. This is 1008, wasn't it? That was the point, the y value at t equals 1. So minus 1008. And it's over h. It's still over h. That's not good. Ugh. What the heck am I going to do about this? All right, the limit as h goes to 0. Let's see. What's 1,000? Let's do like terms. What's 1024 minus 1008? 16. Okay. And we're going to distribute this negative 16 over this mess. Minus 16 minus 32 h minus 16h squared. I just distributed the negative 16, right? Over h. Well, what happens with the 16s? They're gone. So that's the limit as h approaches 0 of what's left. Negative 32h minus 16h squared all over h. Okay, now what's good about that? The h's cancel. So let's cancel out the h's. The limit is the last operator you do. All right, cancel out the h's first. What do you get left? Negative 32 minus 16h. And guess what? This is a plug-in limit for h equals 0, isn't it? This is a polynomial. It's continuous and defined everywhere, so you can just plug in 0. The limit and the function are the same. So plug in and you get, plug in 0 for h and you get, I'm not hearing it, negative 32, right, negative 32 feet per second. So your guess was pretty good. You said, didn't you say 30? Negative 30, that's pretty damn good. But that's the exact instantaneous rate of change at the instant t equals 1 second, while this bowling ball is falling off the building. Okay? All right, now that's known as the derivative at a point. I plugged in a particular number. I plugged in 1 for x, right? But you don't have to do it that way. You could take the derivative of a function at any point and get a function in turn that describes the slope of the tangent lines anywhere along the curve. Let's try that. All right, everyone's got this? Can I move up? Move to the next page? All right, just practicing using the difference quotient definition of the derivative. Okay, what if f of x is x squared? What's f prime? Do you know it, by the way? You probably know this rule, right? You said it. What was it? 2x. All right, let's pretend we don't know that. Where does that, how do you know that? Where does that come from? Yeah, you know the rule, but where's the rule come from? This Pia Negro, is she God? So take this on faith.
Yeah.
This is an oligarchy. The math guy? Oh, okay. Well, guess what? We're going to prove it right now. Are you ready? I want to find f prime of x. Remember what it is. It's the limit as h approaches 0 of f of x plus h. That means plug in x plus h wherever you see x. So plug in x plus h, what do you get? Plug in x plus h in place of x, what do you get? X plus h all squared. Okay, so it's a limit as h goes to 0 of f of x plus h minus f of x. What's f of x? X squared. All over, don't forget this is the problem, all over h. Okay? Now, you know how to FOIL, right? Didn't we just do something like this? So the limit as h goes to 0 of x squared plus 2xh plus h squared. FOIL it out the hard way if you have to. Yes? How did I get what? That's just the definition we made up. Remember, we made this up. Here. Ta-da! It says plug in x plus h into your function you're trying to take the derivative of. In this case, it wasn't x plus h because I was doing a specific value of x. I plugged in 1 for x also. So that's a derivative at a point. But I'm going to try and get the derivative at every point, at every single x. So it's going to be a more general result. F prime here will itself be a function that describes the derivatives everywhere along this curve. That's not what we got here. Here we got one particular derivative at one particular point on this curve. That's a little different. We're using the same rule though. All right, so is it okay where I got this? This is f of x plus h if that's f. This is f of x if that's f. That's it, that's all I did. All right, now this part is the foiling, but don't forget this part. Right? And so the x squareds cancel, don't they? That sounds familiar. That happened when x was 1, so it's going to happen when x is something else too. It's the same pattern. The limit as h goes to 0, let's see what's left. I got 2xh plus h squared over h. What happens now? The h is canceled, just like before, right? Okay, I was doing it for a particular x equals 1, but it's still working out the same way. The limit as h goes to 0 of what? What's left when you cancel out the h's? 2 what? 2x plus h. Is this a plug-in limit for h goes to 0? Yep, you get then 2x. Is that what you expected? Yes, it is. What?
How come for this part it's x plus h squared and not x squared plus h?
Why would it be x squared plus h? Well, okay, this is the rule we're using, right? Look, it says take f of x at x plus h minus f of f at x. What does that mean? That means a composition of two functions. Take x plus h and plug it into f. When I plug in x plus h wherever I see x, that's what I get. Well, then you square it by foiling, but you don't square it directly, no.
So there's x cubed.
X plus h cubed. Yep, exactly. Yep, that's it. In fact, guess what we're doing now? We're doing x cubed. Yes. Okay. All right, let's try x cubed. Try it again. What if, it doesn't have to be f all the time. What if g of x is x cubed? Can you find g prime? And you know what it is. What is it? 3x squared. But let's say you don't know. And how do you get it? The first time you ever saw this, you didn't know this, right? This is how you get it. G prime of x is what? The limit as h goes to 0 of what goes here? X plus h all cubed minus x cubed over h. That's it. This is f of x plus h. This is f of x. That's the rule. All right. So you know how to FOIL, right? 1, 3, 3, 1, x cubed, x squared, x to the 1, x to the 0, h cubed, h squared, h to the 1, h to the 0. Yeah, that's how you FOIL. It's called the binomial expansion theorem. You ever hear that? You know the binomial expansion theorem? Where did I get? Well, look, let's do it again. Over here. 1, 2, 1. X squared, x to the 1, x to the 0. H squared, h to the 1, h to the 0. Same thing. Where did the 1, 2, 1 come from? Where did the 1, 3, 3, 1 come from? Pascal's triangle. Yeah. It's combinatoric numbers. You ever do NCR? NCR numbers? So those are the numbers on Pascal's triangle. The binomial expansion theorem uses NCR numbers? Okay. If you want to do it the hard way, you can always FOIL 2 times. Don't forget what goes here, though. Minus the x cubed. So this 1x cubed and this 1x cubed are going to cancel. All right, just show one step at a time. Don't get crazy. Put your foot in your mouth real fast. You can do like 2 or 3 steps at once. So just cancel the x squareds. What's left? The x cubes cancel. What's left? 3x squared h plus 3xh squared plus h cubed. Don't forget it's still over h. Then you're going to cancel the h's, the limit, as h goes to 0. Remember, this is the last thing you do, so I didn't do it yet, so it's still here. What's left when you cancel out the h's? And is that a plug-in limit for h equals 0? Yep, what do you get? 3x squared. Amazing. Didn't you expect that? You expected that, didn't you? Probably, yeah. Similar. All right, so try it again. What if f of x is x to the 4th? Aha. What's f prime of x going to be? Well, you know. What is it? We're sort of confirming the rule that you take the 4 and bring it in front, and then you take the 4 and subtract, so you should get 4x cubed. Is that true for any integer? What if it's negative 1? Is that true for rational numbers? What if it's a half? We're going to have to talk about that, though. No, I don't know that. This pattern that we're confirming right now is only for positive integers. We didn't deal with negative integers. We didn't deal with fractions. We got to do that. That could be different. I don't know. It turns out it's not. You know this. But I'm not assuming nothing. All right. F prime of x is going to be the limit as h approaches 0 of x plus h to the 4th minus x to the 4th. I didn't need all of this. Okay. All over h. All right, so let's see. Who can FOIL this? The limit as h goes to 0 of. Let's see. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. What's the next line? Do you know how to generate it? 1, 4, 6, 4, 1. What is it? It's the number above plus the number before. The number above plus the number before. Number above, if it's not there, is a 0 plus the number before. So, 1, 4, 6, 4, 1. X to the 4th, x to the 3rd, x to the 2nd, x to the 1, x to the 0, h to the 4th, h to the 3rd, h squared, h to the 1, h to the 0, and add them all up. Wow, that was easy. Was the binomial expansion theorem ever so easy? Now, don't forget, what did I forget? On purpose, what did I forget? What did I forget? I forgot it. Minus x to the 4th is still sitting here. I'm just copying it. Okay? All right, so what do we get? Let's see, the limit as h approaches 0. Now the x to the 4ths are gone, right? 4x cubed h. Does that look familiar? Right? Weren't we expecting this to show up? Plus 6x squared h squared plus 4xh cubed plus h to the 4th. Don't forget it's over h, so now what? You can take out some h's. Okay, so we get the limit as h approaches 0 of 4x cubed plus 6x squared h plus 4x squared h squared plus h to the 3rd. And is it legal to plug in 0 where we see h? So you get what limit? 4x cubed. So if y is x to the n, then y prime is, what pattern are we seeing? What'd you tell me to do with the exponent when it was a 4 n x to the n minus 1? That's the pattern we're seeing. We're not done confirming it, but it seems to be good for positive integers. On Monday, we'll visit negative integers and rational numbers like fractions. Okay? All right, so we're about out of time, so let's just save this. That's all she wrote. Bye-bye.